I'm going to show you how to determine the voltage of an electrochemical cell. The cell that I'm going to talk about is aluminum tin. This is the one that we were talking about in the activity in class. And you had two half reactions. You had aluminum that was going to be oxidized, going to aluminum plus 3 electrons. And at the same time, tin was going to be reduced, plus 2 electrons going to elemental tin. Now, when you're determining voltage of cells, it doesn't matter how many electrons are going on. I don't need to balance the electrons at this point. There are cases where you do have to worry about it, but when we're determining voltage, it's not the balanced equation in terms of electrons that's important. So how do I know that out of these two that aluminum was going to be oxidized and tin was going to be reduced? Well, the way you determine that is with something called a standard potential table, voltage table, and it looks like this. And they come in different varieties. This is the AP one, and so we might as well use that. Sometimes they're put in terms of alphabetical order, sometimes they're reversed, but basically what you have is you have little half reactions all written in the form of reduction. So every one of these is written in the form of reduction. And it tells you for that half reaction what the voltage is going to be. Alright? So, oops, I'm not sure I want to do that. How do I undo? Okay. Anyway, once I draw on this, I guess it's there. So, this particular reduction table puts fluoride on the top, all right, and puts lithium on the bottom. Well, it's easy for me to remember that lithium currently is what a lot of batteries are being developed with. Lithium batteries are really good batteries. And if you look at the voltage on the lithium down here, it's negative. Well, that's because lithium really is a very strong, it wants to oxidize. Now remember, these are all written in form of reduction, where you're adding electrons. So in reality, this lithium at the bottom, where it's Li plus an electron going to lithium, where the value is given as a negative 3.05, in an electrochemical cell, that lithium is going to want to be oxidized, or is going to want to oxidize. So I'm going to flip it. So I'm going to flip the reaction to illustrate a oxidation. And using good chemistry sense, hopefully, if I flip an equation and I have a value, anything associated with it, chances are I'm going to flip that sign. And I do. It becomes a positive 3.05 volts. So it's easy for me to remember who's going to be oxidized. So stronger oxidizers are going down in this table. But like I said, tables can change, so you got to know the meaning of it. Lithium makes a darn good battery. It makes a darn good battery because it wants to oxidize, and the voltage is going to be pretty great. If you can tell from this table, that's about the best potential battery you got. So that means every other combination that I take is going to be reduced, because lithium is the king of the oxidizers. It's going to reduce everybody else. So going back to my example, I'm talking about aluminum and tin. Okay, so I got to find aluminum on here. Well, okay, oops, didn't want to draw there. So okay, go down the list. Where is aluminum? Where is aluminum? Right there. Okay, so right there is aluminum. And now I want to find tin, and tin is right there. Okay, so I have this guy and this guy as my two pairs. Now I already determined that as I go down, the more negative number is going to be the value that will be oxidized, because I'm going to flip it. Alright? So since in terms of this table, aluminum is the better one to be oxidized, I'm going to take the value of the voltage from aluminum, which is 1.66, and I'm going to turn it positive. I'm then going to add it to the voltage of the tin, which is a negative 0.14. Alright? So what this is going to do, so I'll get rid of this. It's kind of weird that it gets rid of everything, but just give me something to do. So okay, erase all this stuff. Get it all out of here because we don't care about any of this stuff anymore. I want something to write on. Okay, so I got all this out of here. In fact, I'm going to take all this out so I can write it up here. So I know that according to what I was doing, that aluminum is going to be oxidized. So back to this, aluminum is going to go to Al plus 3 plus 3 electrons. The voltage from this chart tells me it's going to be a positive 1.66 volts. And at one point that positive came, like I said, because I flipped it, because it's going to be oxidized. Okay? And I determined it being oxidized because it's lower on this particular chart. It's closer to lithium. Could be higher, like I said, but anyway, I won't go into it again. Now, I still need the 10 for the other half, which was, as written, plus 2. I'm having trouble writing that 2. Plus 2 electrons, okay, is going to go to Sn. Well, that's exactly what the half reaction is written as. Okay, it's verbatim. So I'm not going to do diddly squat to the voltage. It's 1.4 volts. Now, this isn't always how it's done, but this is how I like to do it because it just falls out of the electrochemical cell easily. Now I'm just going to add those two together. Alright? So it's going to be, I'm adding them, but really I have to subtract it. It's going to be 2, 5, it's going to be a 1.5 volt battery. Okay, so at standard conditions means all my concentrations here are like 1 molar. So I would have 1 molar concentrations of the ions present, and I would have the anode that would be the aluminum because that is the place of oxidation, and the cathode would be the place of reduction, blah 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 blah. Anyway, I would expect to get 1.5 volts out of a battery. So that is how you use standard reduction tables.